Okay, so hi everyone. As always, I have to go through a couple of announcements and intro slides. First question, is anybody here for the first time? Do you want to say a sentence or two about yourselves, what you work on, so people know who you are? Anyone?
Except Berthy.
Yeah, except obviously the speaker. Yes, everybody. Okay, awesome. In that case, let's go to the first announcement. So the first announcement is a benchmark dataset workshop that this is Adam, your thing, right? Okay, I will just let Adam tell you more about this. Yes.
Hi, everyone. The TDA Bench Workshop is happening here at SkAI in March. And the aim of the workshop is that we are going to look at existing data sets for time domain sources in astronomy, particularly transients. So these are sources that explode, and try to build a new benchmark data set so that we can faithfully compare different algorithms that members of the community are developing to classify these sources, which is a very important and pressing problem on the verge of Rubin and LSST. And so we will be working at this workshop. There will be a small number of talks, only 10 total over the course of the 4 days, because we'll actually be grabbing data sets, pulling things together, and hopefully preparing more or less the entire data set by the close of the workshop on Thursday. If you have any questions, you can, of course, ask me. Registration is still open. There's a small fee, but it'll be here in the SkAI Hub for 4 days, March 9th through the 11th, 12th. It says right there, 9th. It doesn't say right there. Yes, 9th through the 12th. Sorry, 9th through the 12th. Thank you.
Awesome. Thank you so much. Okay, great. So make sure to register for that if that sounds interesting. Okay, the next event that we will have, so next week, February 25th, again, Wednesday, is the SkAI mentoring event. And as I mentioned last week, we have kind of two things happening. There is a mini retreat and then peer mentoring group lunch. So mini retreat is for faculty and scientists. And the peer mentoring group lunch is lunch for everyone with postdocs and everybody who's like early career. We already had one mentoring lunch like this, so similar like before, we want to have groups and touch base within the mentoring groups if people didn't have chance to catch up in between. So again, as always, please make sure to RSVP. If nothing else, we need this to order lunch correctly. So this is next week. After that, March 4th, we have again work in progress. In this case, the project is led by Adam and Han, and we'll hear more about what they're doing and how the project is progressing. But I think with that, I will call Agilas, and then we can go to the main event today.
Thank you. Thank you. So good morning, everybody. It's my pleasure to welcome our speaker today, Dr. Berthy Feng. Berthy received her undergraduate degree, summa cum laude, from Princeton in computer science and minor in statistics and machine learning. She received her PhD from Caltech, working with Katie Bowman. And she's currently a postdoc at MIT, at IFI, a sister institute to ours, a little bit older, the older sister than ours, working there with Bill Freeman. So Berthy is doing a lot of exciting work where she tries to uncover hidden information using priors coming from AI and other sources, and trying to push the limit of computational optics, computational imaging. Today's title is a little bit different than this one, I was told. But with that, please help me welcome Berthy.
Yeah, okay. Thanks for the introduction. Let me go ahead and share my screen here. Send request. Yeah. No, it's okay. Yeah. Okay, cool. All right, great. Yeah, so I'm super excited to be here. And today's talk is a little bit different from the advertised title, but it's going to be all about how we can image at the edge of science by integrating scientific knowledge and AI to recover hidden structure. And I don't know if we can move that cursor somehow. Okay, I got it. Yeah, thanks. Okay. Images drive scientific progress. An X-ray diffraction image known as photo 51 revealed the double helix structure of DNA. Radio images of the cosmic microwave background provide evidence of the Big Bang theory. Prior to the development of diffusion MRI technology, doctors had thought that multiple sclerosis only affected local brain tissue rather than the entire brain network. And there are more discoveries to be made. But many of the most important scientific questions lie at the edge of what we can directly observe. For example, capturing molecular dynamics on short timescales will help us understand which molecules play an active role in certain chemical reactions. Seeing black hole dynamics will help us probe general relativity in the extreme limit. High-resolution fMRI scans of the brain will help us better understand how mental illnesses like depression occur on a neurological level. However, many of these phenomena and many more are currently beyond the capabilities of physical sensors. Today, we'll zoom into my work on black hole imaging and how my work in computational imaging has gotten us closer to being able to resolve a video like this. Computational imaging pushes the limits of conventional optics by incorporating additional assumptions or priors about the object being imaged. This brings us to the central challenge of computational imaging for science, which is deciding what assumptions to impose and how. My work addresses the challenges of this piece of computational imaging. The core idea of computational imaging is that we want to supplement the limited information in our sensor measurements with human-imposed assumptions in order to get an image that's interpretable. The art of imaging lies in figuring out exactly how to impose these assumptions. Let's take black hole imaging as an example. The Event Horizon Telescope, or the EHT, is made up of this global array of radio telescopes. However, the telescope measurements are very sparse and noisy. So when the EHT was working on the first ever image of a black hole back in 2019, they had to impose some bias to get an interpretable image, but they didn't want to impose too strong assumptions as to raise any questions about the scientific implications of the picture. Their efforts resulted in this image of M87 star, which is the supermassive black hole at the center of the galaxy M87. And this was back in 2019. Currently, in the imaging and science communities, we're grappling with how to leverage the increasingly powerful priors that have become available to us through things like generative AI. So my work addresses the challenges of bringing in priors responsibly to do science. I envision being able to turn a knob on the assumptions that we bring into imaging. For example, we can target relatively weak assumptions by bringing in the statistics of a large-scale data set of natural images. Or we can crank up the amount of physics we impose by using a prior based on a model of fluid dynamics. And I envision a framework in which scientists can be able to seamlessly tune this knob between different priors, then evaluate their effects on imaging, and ultimately extract useful insights from the results. In today's talk, I'll present methods that I've developed to support this framework of computational imaging for science. And the talk will be organized in 3 main parts. In part 1, we'll frame the importance of priors when it comes to extreme scientific imaging. So I have a line of work using data-driven priors, specifically through generative AI models, to be able to flexibly probe different assumptions and see how they affect the image reconstruction. Once we've set the stage for the importance of priors, we'll create a tailored approach to bring in the right level of assumptions to tackle a particular problem in astrophysics that's extremely ill-posed. Specifically, we'll look at how we developed an approach that incorporates physics assumptions to recover the 3D dynamic gas near a black hole. However, what if we don't want to have to hand tailor an approach for every new physics-based problem? some physics constraints apply across different settings. So in part 3, we'll propose an approach to flexibly bring in desired physics constraints across different imaging tasks. I also want to mention that I've worked in domains beyond astrophysics, including material science. I have a line of work on physics-based approaches for inferring material properties from videos. But today, I want to focus on astrophysics as our motivating application. So now let's set the stage for the importance of priors when it comes to computational imaging for science. This work was done in collaboration with folks at Google Research, MIT, and Caltech. Black hole imaging is a prime example of the importance of priors. Black holes are a direct result of Einstein's theory of general relativity. They emerge basically when the mass of a black hole curves space-time so much that it traps everything inside of it. So there's this region of no escape known as the event horizon. And if Einstein's theory is true, then we should be able to see this circular shadow surrounded by a bright photon ring representing the event horizon. Before 2019, there had been no direct evidence of such a circular shadow. The Event Horizon Telescope collaboration was formed to be able to capture the very first evidence of this prediction of Einstein's theory. After decades of efforts on an international scale, the EHT released this picture of M87 star in 2019. And this picture advanced science by providing the first observational evidence of a circular shadow as predicted by Einstein's theory of relativity. And it also pushed the imagination of what we imagined could be possible to image. So all in all, the scientific community was pretty excited about this result, but unfortunately, you can't please everyone, especially the average internet user. The abundance of memes made it pretty clear that people thought the image was too blurry. And honestly, who can blame them? Because we're used to seeing these super cool graphic simulations of black holes, like in Interstellar. The visceral reaction that people had to the M87 picture reflects that many of us carry our own assumptions of what we expect to see, and that often means wanting to see even more than what the telescope data can provide. So let's first understand exactly why the first image of M87 star had to look blurry. So although M87 star is extremely large, it's also very far away. It's over 50 million light years away from Earth. So in terms of solid angle, it takes up a teeny tiny fraction of the night sky. Put in perspective, the image of M87 star is about 1,000 times smaller than a single pixel of this image from the James Webb Space Telescope. Putting this in an everyday perspective, it's 10 to the 9th time smaller than a typical iPhone pixel. And this hints at why the first image had to be blurry. In short, EHT measurements are sparse, low frequency, and noisy measurements in Fourier space, not image space. Through a technique known as interferometry, each pair of telescopes in the EHT array collects a spatial frequency measurement in Fourier space of the sky's image. Together, they collect this sparse set of Fourier components. The rest of the Fourier space we have no observations of. Now, we could fill in some of the missing information by completely covering the Earth with telescopes up to some maximum spatial resolution. And if we wanted to get higher spatial frequencies, then we'd have to build a telescope larger than the size of the Earth. However, these are infeasible tasks, so we have to make do with the sparse, low-frequency, noisy Fourier components that we are able to observe. So to give you a sense of how messy this data is, if we were to naively invert it into an image, it would look pretty uninterpretable, like this visualization. And this is where computation comes in. Using computational algorithms, the EHT transformed the raw telescope data into an interpretable image. And this image looks blurry because it's at the intrinsic resolution of the telescope array. And the EHT understandably didn't want to bring in very strong assumptions beyond simple priors like spatial smoothness and compactness. But what if we want to be able to see higher resolution images of black holes? Well, we could try to build that telescope larger than the size of the Earth, but that's likely not going to happen in any of our lifetimes. So to answer important scientific questions now, we rely on computational methods. And in particular, we have to bring in stronger, more sophisticated priors like scientific knowledge and AI. And this is exactly the motivation for the work that I want to tell you about today. We wanted to offer a way to see beyond the blur of the original M87 star image by plugging in different, potentially stronger image assumptions. Using the same real data that the EHT used to give this image of M87 star, we applied different data-driven priors to see how the image reconstruction would change. So one prior was trained on the CFAR10 dataset, which is a computer vision dataset of generic natural objects. As a pathological example, we applied a prior trained on CelebA, which is a computer vision dataset of human faces. Remarkably, a face prior still recovers a ring structure, although one that looks a little bit like the Phantom of the Opera. We also applied a prior trained on GRMHD fluid flow simulations under this model GRMHD, which stands for General Relativistic Magnetohydrodynamics. This would allow us to plug in stronger assumptions about the physics underlying the image. The most constraining prior that we looked at was trained on images from a geometric model of accretion flows under RIAF, which is known as radiatively inefficient accretion flows. And this is the most constraining because it simply parameterizes the image as this geometric ring with a certain size and brightness profile. So each of these image reconstructions is based on a score-based diffusion model that we had pre-trained on the relevant data set. And we refer to each of these priors as a score-based prior. We developed an approach that would allow us to apply score-based diffusion models as principled priors for scientific imaging. And without going into details just yet, the main advantages of our approach are, one, we can target more assumptions than traditional image regularizers. And two, our approach is hyperparameter free at inference time, which is not true of many of the diffusion model-based imaging techniques that have been proposed recently. And the fact that our method is hyperparameter free means that we can apply these priors without fear of imposing too much unwanted additional human bias. Now let's delve more into the details of the approach. Score-based diffusion models are state-of-the-art in the generative modeling of images nowadays. For the purposes of this talk, you can think of a score-based diffusion model as a black box neural network with learnable parameters theta, which, given a data set of training images, learns to generate new images resembling the training data. Effectively, once its weights theta are learned, it defines this learned prior, p theta, which we would like to incorporate as a prior when we do image reconstruction. Now, the really nice thing about score-based diffusion models is that they're probabilistic, meaning we can evaluate probabilities of any images under the learned prior. For in-distribution images, the log probability should be high, whereas it should be lower for out-of-distribution images and images of pure noise. When it comes to image reconstruction, given a set of telescope measurements, we want to find an image that maximizes data fit with respect to these telescope measurements, as well as probability under the prior. We can write this up as an optimization problem over the image X, where we want to maximize what's called the log posterior probability of the image X, given the measurements Y. And by Bayes' rule, we can decompose this into a measurement likelihood term, log P of Y given X, and a prior term, log P theta of X. The measurement likelihood incorporates the sensing system. It says that given a proposed image X, if we were to observe it with our telescope array, we'd get a set of telescope measurements Y hat that should agree with the actually observed measurements Y. As for the prior, we want to incorporate the learned prior of the score-based diffusion model. The first paper we had in this line of work showed that we could use the exact log P theta function for this, but it can get pretty computationally expensive. So in follow-up work, we proposed using the elbow, or the evidence lower bound, of a score-based diffusion model, which amounts to maximizing the lower bound on the log posterior and is much more time and memory efficient. So it's easier to introduce things in terms of reconstructing a single image, but in reality, our approach reconstructs an entire image distribution that you can sample from. Taking a note from variational inference, we do this by modeling the posterior with a generative network Q that has learnable weights phi, and we minimize the KL divergence from this network to the true posterior. once we solve this optimization problem, Q phi represents an approximate posterior that we can sample from. And this is the exact approach that we used to obtain the reconstructions that I showed earlier. And in fact, we can take many samples from the estimated posterior, and we can compute the pixel-wise standard deviation across these samples to get a measure of uncertainty. Here we can assume that any changes in the standard deviation map in the posterior is coming primarily from the prior, because the measurements and the inference algorithm are staying the same. Where as the strength of the prior increases, the standard deviation map should reflect less uncertainty. And indeed, as we move from left to right, we can assume here that the prior is becoming more constraining. And so the standard deviation maps have lower magnitude in the posterior. And I want to emphasize that these standard deviation maps aren't the same as error maps. They're just showing how much variance is in your estimated posterior. And this highlights the importance of being careful with your priors, because you want to be careful not to overly bias your posterior in the wrong direction. But if you're very confident in your assumptions, you can use a more constraining prior. Another benefit of using multiple priors like this is that we can identify image features that are robust to prior assumptions and therefore reliable for scientific interpretation. In the black hole imaging setting, we extracted ring features from the different reconstructions, specifically the diameter of the ring, the width of the ring, the orientation angle, brightness asymmetry, and the fractional central brightness. And here we show the mean and standard deviation of these features across posterior samples from the different priors. Accounting for error bars, we found that the diameter, orientation angle, and brightness asymmetry were relatively robust to the choice of prior. For example, all priors agree on a range of possible diameters, roughly between 35 and 48 microarc seconds. On the other hand, the width and the fractional central brightness are more sensitive to the choice of prior. In particular, the GRMHD prior gives us the thinnest rings with the highest brightness contrast ratios. The takeaway here is that by applying multiple different priors, we can get a better understanding of which features are robust to prior assumptions. I also want to briefly mention that our work extends to being able to infer videos of black holes from EHT measurements. This work was led by Bingliang Zhang, who's a PhD student at Caltech. For this example, we simulated measurements of Sagittarius A star, the black hole at the center of our galaxy, and it evolves much more quickly than M87 star. For the reconstruction, we used a video diffusion model that had been pre-trained on GRMHD simulations. This is a simulated result, and soon we plan to apply this method to real EHT data of Sagittarius A star to help us get closer to being able to extract dynamical structure from this black hole. Yes?
So in the previous slide, when you had these, when you were looking at these error bars and, sorry, thank you. So maybe you covered this already, but are these, is there a ground truth that you're comparing against to kind of understand how much these vary, like the error bars that you have in these plots? Is there a ground truth that you could use to figure out,
Yeah, so we don't know exactly the ground. I mean, I think the theoretical estimate of M87 star is that it has a diameter of about like 42 microarc seconds. I think that's the right value. And so these error bars are just telling you that, yeah, that theoretical estimate is within the range of estimated diameters based on these images. So beyond that, I don't really think that we have like a ground truth estimate beyond theoretical predictions.
Okay, but these bars are more of the variances of the images that you constructed.
Of the images that we reconstructed, yes. Yeah.
So so it's about how the posterior sampling variance looks like.
Yeah, exactly. Yeah.
Thank you.
Okay.
Perhaps we could go to a question on Zoom since we're...
Yeah, I saw that there was a question about why it wasn't centered.
Yes, that was the question.
So the reason that it's not centered is because the EHT measurements actually don't constrain the position of the ring. So we use what are called like closure phases. And so no matter how you shift the image, the closure phases are going to stay the same. And so that's why the measurements don't constrain the position of the ring. But because the GRMHG and the RIAF priors were trained on images that were all already centered, that's why we get a reconstruction that's centered, whereas CFAR10 and SLEB-A contain kind of various images with like different amounts of compactness and centering. And so that's why you see it a little bit off center.
Thank you.
Yeah.
Does the lack of centering in the two left priors affect the standard deviation maps as well? Like, can they move around when they're in there?
Yeah, totally. I think so. We did a little pre-processing on these data sets to make them a little bit more compact. Otherwise, it would just be like all over the place. But that's why you see in the standard deviation map that there's like a little bit of shifting going on in terms of exactly where the edges of the ring are. Yeah. Okay.
Another question.
Yeah. Oh. Okay.
Yeah. So in this way that you're sampling from the posterior, do you think that that like process is, should I be able think of this as, you know, whatever you're doing is able to essentially sample from the true posterior given the prior? Or do you think that there's some room for improvement, like computationally, to get that close to the right statistics? Like how, even if the prior was absolutely correct, like how much can I trust the standard deviation of the measurements from this sampling procedure?
Yeah, so that's a really great question. I think that we're still, like the community is still trying to figure out how we can use diffusion models to sample a true posterior. So I will say that this is a formulation that will get you to a true posterior, the closest posterior in a KL sense. And what we found is that we're limited by the modeling capacity of this network, Q-Phi. So we used like a normalizing flow for this, but that's not the most expressive generative model. And so we found that we were kind of limited in the expressivity of the posterior that we would estimate. So if you think that your posterior is going to be like super multimodal, have like really detailed features, then perhaps this network would limit you from capturing that full posterior. So yeah, that's a great question. But I think that this formulation is kind of nice because it allows you to kind of think about, okay, where are the modeling gaps and exactly where are we missing out on being able to model the true posterior? And then also modulo any like optimization errors, like just, you know, how well you can optimize this. Okay. Okay, maybe I can move on if there are any other questions. Okay. Okay, great. Yeah, thanks for the questions. I think that about covers what I wanted to talk about in terms of really framing the importance of priors when it comes to imaging. Sorry, was there one more question here? Yeah.
Yeah, so maybe just a clarification. The natural image data sets don't seem to have an image formation model that is in any way obviously connected to black hole physics. So are they around just to demonstrate the technique, or is there some scientific value there?
So the scientific value here is like it represents a prior where you're not baking in any assumptions of the physics. So it represents like a simple natural image statistical prior. So the only thing you're assuming here is that like the black hole image would incorporate statistics that you might find in a data set like CFAR10. Yeah.
Aren't you baking in some really weird physics prior, which is the evolutionary process that led to human face appearance? Which, how is that related to black holes?
Yeah, to some extent, yes. I think the point here is that you want to be able. Okay, so how do I phrase this? The point here is just showing that you can like probe different assumptions, right? And even if some assumptions don't really make sense, like I don't think anyone would argue that the SLEB-A prior would make sense for this application. But it's showing that like even if you put in this like totally pathological prior, there are some features that are still going to appear that should make you pretty confident that they're coming from the measurements rather than from the prior. And then also, when you are using a prior that's based in physics that you can trust more, then you can maybe trust the prior related features that are coming out in that reconstruction more. Yeah. Okay. So now I want to shift towards the physics-based side of this knob, where we recently proposed an approach where we carefully incorporated physics assumptions to tackle an extremely ill-posed problem in astrophysics, which is reconstructing this dynamic 3D gas. And this work was done in collaboration with Andrew Chayel, who's an astrophysicist at Princeton, as well as collaborators at the University of Toronto and Caltech. So far we've been looking at static 2D images of emission coming from a black hole accretion flow. Such images help us answer questions like, does general relativity accurately predict the appearance of a circular shadow? But such images are just an incomplete snapshot of the complex 4D spacetime near a black hole. If we can recover this type of dynamical 3D structure, then we can answer interesting questions like whether general relativity accurately describes dynamics near the black hole. So I'll set up the exact inverse problem that we're trying to solve here. Say we have this following simulated 4D emissivity field of the gas revolving near a black hole. Here is what that emissivity would look like from our point of view on Earth, if we had perfect vision, that is. And what we see is a projection of the 4D emissivity onto the image plane. The projection is the result of a complicated process here, where light follows these curved ray paths known as geodesics. And these geodesics are curved because of the way that the black hole is so massive that it warps space-time around it, bending light. And unfortunately, we don't get to observe the image plane perfectly. Instead, we have sparse EHT measurements. Here's a visualization of the time-varying measurements that the next generation EHT, or the NG-EHT, would capture of this emissivity field. Now, our task is to go from these super sparse measurements to a reconstruction of the original 4D emissivity field. So this amounts to doing a 4D tomography problem. And this tomography problem is different in many regards from traditional tomography problems like computed tomography and 3D scene reconstruction, which typically assume a static object, multiple viewpoints, and straight light paths. In our setting, we have an evolving source, so we can't simply aggregate measurements across time. We have a single viewpoint, which obfuscates 3D structure. Light follows curved ray paths instead of straight ones due to the warping of space-time from the black hole. And on top of that, there is an additional unknown in exactly how the emission appears on the image plane as a result of Doppler boosting. And finally, we have extremely sparse measurements from the single viewpoint. All of these challenges combine to make our problem severely ill-posed. And we propose to constrain the solution space by carefully incorporating scientific or physics knowledge. So talking with Andrew Chayel, our theoretical astrophysicist collaborator, we decided that there were some physics assumptions that we could be very sure about and others that we wanted to be more flexible about. So we could be sure about geodesics and the exact geometry of the ray tracing that should go into our image formation model. And we also could be sure about the EHT measurement system because the EHT collaboration has already written very good simulation code for this. Now, what we couldn't be so sure about was the dynamics near the black hole because this is the very property that we're trying to reconstruct. So we developed an approach that would incorporate the known assumptions as hard constraints while leaving room for learning about the unknown dynamics by enforcing them as soft constraints. In fact, we impose dynamics as a soft and learned constraint by jointly recovering a 3D velocity field in addition to the emissivity field. This velocity field describes the dynamics of the emissivity. It also goes into the measurement forward model by influencing exactly how bright the emission should appear on the image plane as a result of Doppler boosting. So there was a previous method that had been proposed for this type of task, but it was not suitable for our setting because it prevented learning about the dynamics near the black hole. And this previous method is known as BH-NeRF or black hole NeRF. The way it works is that it estimates the initial 3D emissivity field, and then it propagates it according to a Keplerian velocity assumption. The Keplerian assumption says that everything orbits at a fixed radius, but we know that this isn't true near a black hole because sort of a defining feature of black holes is that things are falling inward and moving towards smaller radii. So this brings us to the first limitation of BH-NeRF, which is that the Keplerian assumption breaks down near the black hole, and because it's imposed as a hard constraint, we can't overcome any errors in this assumption. Another limitation is that because BH-NeRF only estimates the initial 3D emissivity field, it cannot account for new flares of emission that pop up over the time frame that we're trying to image. So we propose physics-informed dynamic emission fields, or PIDEF, where we reconstruct a time-varying emissivity field as well as a learned velocity field. This allows us to overcome any errors in the assumed velocity model. And because our emissivity field varies with time, we can recover any new flares of emission that appear over time. Now let's take a look at the approach in a bit more detail. Inspired by neural radiance fields, or NeRFs, we model the 4D emissivity field with a neural field via a coordinate-based neural network. So the input here is a time coordinate in 3D spatial coordinates, which are mapped through a positional encoding, and then through a multi-layer perceptron, or MLP, which outputs a scalar emissivity for every point in time. Similarly, we model the 3D velocity field with a neural field, which takes as input the 3D spatial coordinates and outputs the 3D velocity for every point in space. And then we jointly optimize both of these networks according to 3 objective terms. The first is a data fit loss, where we take the estimated emissivity and we simulate what the NGEHT would observe. So this gets us predicted measurements y hat, which we compare with the actually observed measurements y, and we want to minimize the difference between these two. The velocity network also goes into the measurement forward model by influencing the Doppler boosting factor, as I mentioned earlier. Second, we have a dynamics loss, where we take the current estimated emissivity and then we propagate it forward in time using the ODE given by the estimated velocity. We compare the ODE prediction with the emissivity network's prediction for the next time frame, and we want to minimize the difference between these two. Third, which is not visualized here, we have light velocity regularization, where we supervise the velocity network with a predefined velocity prior, which could be Keplerian, for example. But this velocity regularization, we ramp down to essentially 0 by the end of optimization. So now let's take a look at an example of results. So here we simulated a 4D emissivity field using a predefined hotspot model and predefined velocity model. Here is our reconstruction of the gas emissivity field. And we compare to a physics agnostic baseline where we just fit a 4D MLP to the given data. Here are a couple still frames for easier comparison. So the thing to note is that our reconstruction better localizes and resolves the blobs of emission, and in particular shows better how it's moving in towards the black hole. So you can kind of see this in the bottom row, how we're capturing more of the spatial structure of these blobs of emission and how exactly they're rotating in towards the black hole. We also compared to BH-NeRF, which is the previous method that I mentioned earlier. Now, the emissivity structure given by BH-NeRF is completely different because this method is desperately trying to fit the incorrect Keplerian velocity model. Moreover, BH-NeRF only estimates the initial condition, which is why you mostly see the initial emissivity being smeared out over time. So in terms of peak signal to noise ratio, or PSNR, our results are overall quantitatively better as well. And the main reason for the improvement in the emissivity reconstruction is that we jointly recover the velocity field. So here we show the radial velocity and the azimuthal velocity on the 2D accretion disk, which is the disk on which the emission is orbiting. Here's our reconstruction of the velocity fields. In comparison, BH-NeRF assumes a fixed Keplerian velocity model. And The physics agnostic approach, the 4D MLP approach, doesn't make any assumptions about the velocity. And so you can see that our velocity reconstruction is much closer to the ground truth. And crucially, we didn't start by assuming the correct velocity model, but our method was able to recover the correct one. So this work really highlights the benefits of inferring dynamics. First of all, it leads to more accurate video reconstructions to begin with. And this lesson can be carried across other domains, including computer vision. By reconstructing the velocity field, we can also open the door to measuring more physical quantities, like the spin of the black hole. Right now, scientists don't know the spin of Sagittarius A star. So it would be great to be able to constrain this parameter so that we can better understand how to study this black hole. And ultimately, this would lead to astrophysicists getting closer to being able to probe fundamental physics models in this extreme region of the universe. Okay. So that wraps up the second part of the talk.
Maybe I can read the question.
Yeah.
So this question is, what type of positional encoding is used? Would different input encoding influence the sharpness of the reconstructed image?
Yeah, so we use the same input. We use the same positional encoding that BH Nerf used, which is like a sinusoidal encoding with, the degree was like 3. We didn't really play around too much with it. We didn't really find that it was too sensitive to the positional encoding. Okay. So in that example, in the second part, we really had to like handcraft a physics-based approach to this particular problem. But there are some physics constraints that apply across problems. So we don't want to have to handcraft approaches for every new physics constraint that we could dream up. So in part 3 now, we'll discuss how we can bring in physics constraints more flexibly across different inference tasks. This work was done in collaboration with Ricardo Baptista, who's now at the University of Toronto, and Katie Bauman, who's at Caltech. Some physics constraints apply across problems. Conservation laws, partial differential equations, symmetries, these all apply across many different types of data. The question we sought to answer in this work was how we can apply a desired constraint generally across different data sets without having to hand tailor an approach for each problem. To illustrate things, I want to show you everything in terms of a 2D example rather than images. So what do I mean by a constrained data distribution? Well, suppose we have these points in R2 that dictate some sort of data distribution represented here by the gold stars. And this distribution is constrained in the sense that it lies in a constraint manifold, which we'll call M. To give you a concrete example of what M might be, if I want these points to be valid probability distributions, then M could be a 2D simplex so that all the points values sum up to 1. This is just an example. And now let's say that we have a certain inference task, which we'll say is generative modeling. And let's say for the sake of illustration, that our generative model is going to be a diffusion model. But the ideas will carry across different types of inference tasks and different types of generative models. So if we were to train a diffusion model on this data distribution, we would want it to also satisfy the constraint. But in reality, due to learning and sampling errors, we could easily get samples that some of which fall on the constraint manifold, but others fall off of the constraint manifold, deeming them invalid. And so what if we could somehow transform the constrained data points into an unconstrained space? This would make our problem a lot easier. Because then, okay, yeah. So actually there exists something called a mirror map that does exactly this, which transforms the constrained data space into an unconstrained data space. And there exists an inverse mirror map that puts us back in the constrained space. And then what we can do is we can train our diffusion model in the unconstrained space and sample from it there, but then map its generated samples back to the constrained space via the inverse mirror map. So this is a really neat idea, and this is the basis behind mirror diffusion models, which were proposed in NeurIPS a couple years ago. But unfortunately, analytical mirror maps only exist for convex constraints and they're hard to derive in general, even for convex constraints. We wanted a way to handle arbitrary constraints, such as maybe a partial differential equation from physics. So in that case, how would we define a mirror map and how would we define the inverse? We proposed neural approximate mirror maps, or NAMs, where we replace the analytical mirror maps with neural networks. One neural network, G-phi, models the forward mirror map. Another neural network, F-psi, models the inverse mirror map. And then the question becomes how we can train both of these networks jointly to define an ideal mirror space. So our work proposed a joint training procedure that consists of 3 terms. The first is a cycle consistency loss, very similar to the one proposed in CycleGAN, where we ensure that G-phi and F-psi are inverses of each other, or at least as close to inverses as possible. And the second is a constraint satisfaction loss, which encourages the inverse mirror map to output images that are close to the constraint set. And finally, we have regularization to ensure a unique solution. And we simply encourage the forward mirror map to be as close to the identity as possible. So once these networks are trained, they define a learned unconstrained or mirror space. So then we can map our training examples into the unconstrained space and then train a diffusion model in the learned mirror space, sample from it there, and then map the generated samples back to the constrained space via the learned inverse mirror map. And I want to note that, again, this illustration doesn't just apply to diffusion models. You could train any generative model like a VAE or GAN in the unconstrained mirror space. And it also doesn't just apply to generative modeling as a task. The main idea of this approach is to somehow move our constrained space into a space where they become unconstrained, where we can solve our inference problem. So we validated our approach on a variety of constraints now defined on image data sets. One simple constraint we looked at was on the total brightness in the image. And this is relevant for black hole images because we can often assume that we know the total flux in the image. So here's a sample given by our approach. The baseline approach is a vanilla diffusion model that's trained on a data set of images that already satisfy the constraint. And the thing to note here is that visually speaking, both of these samples are nearly indistinguishable. However, if we look at the histogram of constraint distances of the generated samples, we can see that ours in orange are much closer to 0, meaning they're closer to satisfying the constraint. We also look at a constraint under a 1D Burger's partial differential equation. We also looked at a constraint on 2D Kolmogorov flows being divergence-free. We looked at a geometric constraint on the spatial periodicity in the image. And we looked at a semantic constraint on the number of objects in the image. Note how in each case, our mirror map approach does a much better job at satisfying the constraint than the baseline approach. An application that I'm really excited about is to use neural approximate mirror maps as a way to obtain physics-constrained and data-driven priors to solve inverse problems. We demonstrated this on some data assimilation type tasks. For example, let's say that we observe 2 noisy states of a Kolmogorov flow, and we want to infer the missing states. We can recast this as an imaging problem of denoising the given states and inpainting the rest of the image. Crucially, whatever velocity field we recover should be divergence-free to represent an incompressible fluid, which means that whatever flows into a region has to flow out at the same rate. Now, the baseline approach here is to train a diffusion model on a data set of divergence-free velocity fields, and then use an off-the-shelf diffusion-based inverse solver like DPS, which stands for diffusion posterior sampling, to solve the inverse problem. And so here's an example reconstruction where the vorticity field is shown in the first row and the divergence field is shown below. In contrast, our approach trains the diffusion model and runs DPS in the learned mirror space and then maps the solution back to the divergence-free space via the learned inverse map. And again, you can see that visually speaking, the vorticity fields are nearly indistinguishable from each other, but the divergence field is much closer to 0, meaning that our solution is more physically accurate than the one given by the baseline. So the takeaway here is that neural approximate mirror maps can be a great way to solve physics-constrained inference problems across different types of data sets. So I hope that these three sections of the talk have given you a flavor of the types of methods that I develop and how they support the framework that I envision for computational imaging for science. And I do want to note that a lot of the insights extend beyond astrophysics to other domains in the physical sciences, like materials science. So I want to briefly talk about the line of work I have on materials science, which has been done in collaboration with material scientists at Caltech. So one work known as visual vibration tomography proposes a way to reconstruct the spatially varying Young's modulus and density values throughout a 3D object, given a video of just its surface vibrations. We hope that this can be useful for non-destructive testing applications. More recently, we have a work called visual surface wave elastography, which predicts the tissue thickness and Young's modulus across the human body, given just a video of motion observed on the skin. And we hope that this can be useful for applications in at-home health monitoring. And I want to continue to develop novel techniques to extract physical parameters from everyday visual data like videos. I've also applied my methods to medical imaging, including compressed sensing or accelerated MRI and photoacoustic tomography. So in my future work, I want to continue to build out this framework of truly science-driven computational imaging, where scientists can easily tune a knob between different priors, then evaluate their effects on imaging, and ultimately extract useful insights from the results. And there are important challenges to tackle in each of these stages. First, we need to expand the palette of priors that are available to us. And I propose to do this by tightly integrating physics and AI. I want to work towards a unified imaging framework where we can combine physics and AI into a unified prior that we can then plug into an imaging algorithm. This can also be useful for foundational AI by creating physics-informed AI models that are more robust and data efficient than the AI models that we have now. In terms of evaluating the effects on imaging, we need more interpretable methods for uncertainty visualization. Right now, the way we do uncertainty visualization of image posteriors is the way that I showed you earlier with pixel-wise standard deviation. But I want to move beyond pixel-level uncertainty to feature-level uncertainty. So how do we extract semantically meaningful features from image reconstructions and quantify their uncertainty? This can also help us better understand how different scientific assumptions lead to different image features, and also discern whether image features are coming from the prior, meaning they're hallucinated, or coming from the real measurements. And finally, I want to close the loop by using insights gained from imaging to inform the design of new sensors and to strengthen the root of scientific understanding. So computational imaging also involves co-designing sensors so that we can better target certain image features. So far, co-design has focused usually on being able to optimize for a single downstream task like classification. But if we can somehow bring in the insights through feature-level uncertainty visualizations, perhaps we can think about designing new sensors to target certain semantic image features. Another way to close the loop is to update our physics models through imaging. And I propose to do this by building more feedback loops between physics models and images so that they can inform one another. A great example of this comes from my work on black hole emission tomography, where we reconstructed the unknown velocity field. And we can scale up this idea to more physics parameters and also think about how we can completely rethink physics models through the imaging process. So at the beginning of the talk, I presented you with some examples of scientific phenomena that we would like to image and how computational imaging can get us closer to being able to image these phenomena. And I'm optimistic that computational imaging can help us answer important scientific questions now by bringing the invisible into view. Thank you.
The questions. Oh, do you want to guide the questions?
Oh.
He help out with the others.
Mm-hmm.
Yeah. Any questions, please? I didn't know.
I think there was another. Did I miss one on Zoom?
I can read one from. Yes, I can. Okay, maybe we can start with that one. So The question was for part 2, physics-informed neural field, how to balance the data fit loss and the physics ODE loss.
Oh, yes. So that requires some hyperparameter tuning. Yeah, we did kind of a hyperparameter sweep between different combinations of data fit loss and the dynamics loss. And so when it comes to thinking about applying this to real data, what we would probably do is do this sort of hyperparameter sweep on some simulated data and see what would get us the most accurate reconstructions. And then we could apply whatever hyperparameters we get out of that to real data.
Thank you. Actually, there was
go.
there was another comment before. I think that was, which is interesting. So I wanted to see if you have any comments on that. I think that was even before when you were just talking about images. So the comment was, there are papers that discuss that Bayesian uncertainty quantification from posteriors would overconfidence uncertainty collapse in some cases. I'm curious, how do we know the uncertainty is trustworthy if the ground truth is not available?
Yeah, that's a big question, and I think still an open one, which I think kind of gets back to the question that was asked earlier about whether we know if we're like estimating the true posterior. Right, I don't have a great answer to that, but I do know that like I have a pretty good sense of where the gaps in the posterior estimation are coming from, at least from our approach, which are the choice of the variational distribution. So the expressivity of the variational family that you choose to represent the posterior, that's going to dictate kind of the maximum expressiveness that you can capture in the posterior. And then also any optimization errors. So you want to be sure that you're finding like a global minimum in that KL divergence optimization problem. Beyond that, I think it's a really excellent question.
Thank you.
Yeah. Oh, if I may, on the previous question of the, can I ask questions also? Okay. No, on the previous question of how you balance fidelity to the data and the prior, because you said at some point it's hyperparameter free, but by and large you want to weigh the contribution of the prior knowledge, right? You don't want is there an example where it's hyperparameter free when it comes to the relative distribution? Is that like when you try to match the prior, that then the weights are one for each term? Is that what you meant?
Yeah, basically. So like when I said it was hyperparameter free, so our method just exactly follows the Bayes rule, and we don't have any like weights on the prior versus the measurements. We just take, Bayes rule gives us this,
right. No,
yeah, the two terms, and then we can just exactly compute what the prior probability is using, either the exact log probability or the elbow. And that's what I meant by it being hyperparameter free.
All the examples you showed there varying the different priors was under this assumption, right?
Yeah, so everything had a weight of 1.
Yeah. Okay. Okay.
Yeah.
Thank you.
Yeah.
Hey, thank you for the great talk. I was wondering about the neural approximate mirror map. So when you showed the divergence of your method, it looked near 0, but not quite 0 everywhere. I guess my question is that sort of a fundamental limitation, or is that something you could solve with a bigger, more expressive mapping network?
Yeah, so that's a great question. So our neural approximate mirror map approach is ultimately a way to enforce soft physics constraints. I do think, and this is a bit of speculation, but I do think that there's probably like a fundamental limitation to be able to get to like a hard constraint through this type of mirror map approach. So we can only guarantee that we can get hard constraint satisfaction for, well, actually, now that I'm thinking about it, for a convex constraint like divergence free, there should exist an invertible mirror map. So I think that would actually be really interesting follow-up work as to how to ensure that that is actually met for a convex constraint. But for general constraints that aren't convex, it's not necessarily the case that we would get a truly invertible mirror map. And only when there exists like a truly invertible mirror map can we get that exact constraint satisfaction. So I think this is like a really exciting, just like broad area of research about like how to bring in physics constraints into AI. Like another avenue is to think about how we can build architectures, like just build constraints into the architecture, but that requires more hand tailoring for each physics constraint.
Thank you.
Yeah, thanks.
I was wondering if you could, sorry.
Oh, yeah.
Hi. I was wondering if you could speak a little bit about some of the differences and whether or not that leads to additional challenges of applying this to other domains or fields. In particular, I'm thinking about like, so EHT is, we're observing in Fourier domain, and then we're reconstructing the image, and there's a very natural place to put those constraints in there. Or things like we have a good model for the EHT system, but so other domains that maybe we're not working with Fourier data, or we don't have a good model of the system.
Yes, good question. So I will say our method works, it doesn't really make many assumptions on the forward model besides the fact that it's known. So I think the fact that it's in Fourier space for the EHT isn't a critical assumption here. So like, as long as you can write down an expression for the forward model, and as long as you can write down an expression for the measurement likelihood, the method that I showed in the first part of the talk is going to work. Of course, there are cases where you don't know the forward model exactly, and that requires some modifications to the method. So actually we had, I've been working with some collaborators on a more recent project to tackle blind tychography, which is kind of this case where we don't exactly know the forward model. So it's like a blind inverse problem. And you can kind of modify it so that you're also updating the forward model along with the image reconstruction, but it's not going to be as like straightforward or plug and play as the way that I presented it in the first part of the talk.
I'm curious for the mirror maps. Do you include the constraint restoring forward model in the diffusion model training process so that the diffusion reconstruction target is in the original data space, or do you make the reconstruction target in the unconstrained data space? And is there a difference that matters between these two?
Yeah, so in our approach, the diffusion model has no knowledge of the constraint. It's just like we take the mirror map that we've learned, we map our training data into this new space, and then we just train the diffusion model on that space, like as you would a vanilla diffusion model. There is an alternative way to approach this, which is where you like add the constraint loss as like an additional training loss while you train the diffusion model. But that brings in a lot of challenges. One of which is the fact that it would require you to actually sample from the diffusion model while you're training it so that you can evaluate the constraint satisfaction of those samples. Or if you wanted to evaluate like constraint satisfaction of noisy images during the training process, then that might not be the most informative because some constraints might be really sensitive to noise, like a PDE constraint. So we actually did have a baseline though when we did that data assimilation experiment. We had a baseline where we ran DPS with a regular diffusion model, but then we added the constraint as like an additional penalty term in DPS, and we found that even that wasn't sufficient to get images that would satisfy the constraint.
Thanks.
Yeah, thanks.
I think it's a good time to. All right. So thank you very much for the wonderful talk.
Thank you.
And this is the great.
Yes, thank you.
And,
Thank you.
yeah.